Hello everyone, I hope you all are doing well. This side Priya Bhatia, and in this video we will be discussing the hands-on implementation of PCA. We will try to take the diabetic data. If you remember in our journey of learning logistic regression in our previous module, we have taken the similar data set. I'll try to take the same data only in this particular use case. I'll just try to demonstrate you. If you remember, with respect to that data, we have 8 features available with us. So we will try to find out the 2 or 3 principal components. Major focus is on that how basically, if let's say I want to use the sklearn framework to fetch the model, how can we use that? So that is the overall discussion we will make in this video. So without wasting any time, let's get started. So now you can clearly observe here, as I told you, we will be taking a diabetes.csv file. So the very first step, I think you all are aware that we are trying to import all the required frameworks which we will be used to finish this part of PCA. So as of now, I have tried to import pandas and numpy, and we have taken diabetes.csv. The only reason is you are already aware about this data set, and that's the whole idea. If you can see here, we will be having again almost 8 number of features: pregnancies, glucose, BP, skin thickness, insulin, BMI, diabetes pedigree function, age, and the final outcome is the target column is the outcome, which is indicating the either value as 0 or 1. Now, just make sure that here I have skipped the step of EDA. Why is that so? Because I already have explained in a great detail when I was covering up a module of logistic regression that how end-to-end EDA will be done on top of any kind of a data. And if, as far as I remember, I have taken the same file only and I have shown you complete illustration of EDA. So intentionally, my focus is not to repeat that part. I am skipping that step and directly I am trying to showcase you here that how basically the PCA working will be done. So please make sure that you have to do that step before jumping towards this part, okay? So what I have done directly here, you will be able to observe. I have not done outliers detection. I have not removal of outliers. If you remember, insulin contains the highest outliers in this data, right? But I'm not focusing on that aspect as I told you. So here we have tried to see in the description of this data. Why? The objective is to check it out. If you remember, the very first step is to check that whether our data is in a standard normal form or not. So descriptive stats will provide me the idea that whether the mean is 0 or not, whether the standard deviation is 1 or not. So this basically step will provide me the descriptive, I would say, statistics of a, I would say, given data point. So now what will happen? You can see that the mean of all these features which we will be able to get here is not at all equal to 0. And even if you will be able to observe, the standard deviation is also not equal to 1. So what we will try to do is, what is the very first step? If you remember in the last video, I have shown you how manually we can try to find out the PCA components. So in the very first part per se, I'm doing that only. So what we're supposed to do, first of all, we will try to drop the outcome because we are anyhow not working with that. This is the output feature. So we have just in our data points tried to take the input features only. So what we can do is we will first of all try to apply the standard scalar form. So what will happen with the help of this step, we will try to convert the data into standard scalar form. What is the literal meaning of that? The mean is equal to, I would say, 0, and standard deviation is something which is equals to 1. This is the major thing which we are trying to do here. Now, if let's say we will move ahead, you can see this is the same step I have done in my previous videos as well. We have tried to apply a fit_transform part on whole data, and that is where we will be able to get a scale data now. So if you will be able to see the description of this scale data that we have, you will be able to see anyhow the mean is approximately equals to 0. Don't get confused, it is exponential of negative 17, so it is approximately equals to 0 only. And again, you will able to observe our STD value is 1, standard deviation is 1. It indicates that now we will be having a situation where we are having a data in a standard normal form, right? Now, again, you can see the shape of data. What is the second step? You remember, second step of finding the PCA components is to find the covariance matrix. So if you remember, I have talked about 3 approaches in our previous videos, but here I have used a single approach, which is whatever data points you have, do the transpose, then do the matrix multiplication with the original data that you have divided by number of records minus 1. So in this case, we will be having 768 number of records. So what we are doing is, we are trying to do the division by 767. So here, if you will be able to observe, we will be able to get the covariance matrix also. What is the third step? With the help of this covariance matrix, now we will try to figure it out. How many number of eigenvalues and eigenvectors we have? Now it's quite obvious. If you have 8 features separately, definitely you do have 8 eigenvalues and 8 eigenvectors in that case, right? I hope it makes sense. So now, if you will be able to observe, we will be able to apply that linear algebra, framework, or you can say method. Inside that, we have a function name called as EIG, which is basically responsible to give us the eigenvalues and eigenvectors corresponding to the covariance matrix which we are passing. So here you can see, with the help of this particular NumPy package, we will be able to get the values of eigenvalues and eigenvectors. Now, if you can see, we will be having 8 eigenvalues available with us. Now, if you remember, higher the eigenvalue, it means higher the information that corresponding eigenvector will provide to us, and we will take that as PC1. Do you remember that? So in this case, if you can see what is the highest eigenvalue, you can clearly see that 2.09711 is the highest one. So it means that we will definitely take that corresponding to that eigenvector to give us the value of PC1. What is the second PC2? I think second PC2 will become the eigenvector corresponding to 1.733. What is PC3? PC3 will become the eigenvector corresponding to 1.03. What is PC4? I would say PC4 is something which is corresponding to 0.87, and so on. I hope you get the sense. So we will try to check which particular index or which particular value is highest. Corresponding to that, what is the eigenvector, and we will be able to easily create the principal component corresponding to that. Now always remember, PC1 contains the highest information of all the features, followed by PC2, PC3, and you can create until PC8 because you have 8 features all in all. But definitely the main purpose to reduce the dimensions, so we usually try to have the number of components 2 or 3 or 4 depending upon the optimal value. So here you can see we will be having eigenvectors, and as I told you, 0th index contains the highest eigenvalue. So we will take all the rows and 0th eigenvector, and we will try to create the PC1 component. So what we will do, we will try to do the cross multiplication of our original data, which is data scaled, and the eigenvector corresponding to 0th index. So we will be able to get the first principal component. So this is something which we have as a PC1. Similarly, you understand that second PC2 will become this one wala thing. And let's say if you want to create PC3, so how will you create? I think it is quite simple. For PC3 component, you will try to do the again eigenvector, but now you will do with 0th, 1, 2, 3, 4, 5, 6, 7. So I believe you have to take the complete 7th column value of eigenvector because that contains the third highest eigenvalue. So this will be our PC3 component, and accordingly you can create 4th, 5th, and so on. Now the question is, this is something which I think for a raw data I have already shown you in the very first video, right? But via sklearn, how can we create the same thing? How can we generate the same principal components? It's very simple. So inside a package of sklearn.decomposition, so if you want at your end, I would suggest try to read out this decomposition PCA documentation. In this you will be able to see that we will be having complete idea about how PCA works, what are the number of parameters we have, what every parameter indicates. The main parameter in this PCA function is n underscore components, which indicates how many number of PCA components you want to create. For example, in this case, you can see we have directly imported this PCA, which internally is doing the same task which I have just now shown you, right? After that, you can call this function. As of now, let's say we are saying that just create only three principal components. And then we are trying to transform it on a complete original data that we have. So let's try to understand that is that similar or not. There is a negative difference which you will be able to observe, because usually internally they just multiplied it with -1. But anyhow, if you will just focus on the values, absolute values, it will be same. 1.06, you can see 1.12, 1.12, 0.39, 0.39. So you can just verify, even if you will just mention number of components as 3, and again you can just try to verify, you will be able to see that the third principal component is exactly same, right? So what I'm trying to convey here, internally when you are calling this PCA, always remember the same steps, those 3 steps that we have covered up majorly will be working. Checking off or converting into, you can say, having a certain normal form, getting a covariance matrix, creating eigenvalues and eigenvectors, and then finally getting that principal components. Same thing is happening here. It's just that here already developers have written a code and you're using that code to directly get the PCA components, but same values you can clearly see now, right? Now the question which you can ask from me is that, Priya, how we will be able to get an idea that what is the optimal number of principal components which we can create so that maximum information will be retained, because we don't want to lose the data. We don't want to lose the information of a given data. So how basically we will get to know that, okay, this is the number of components which we can take for this particular data set. That is where the concept of explained variance ratio came into picture. So whenever you are trying to create a model of PCA, you can call this function of explained variance ratio, which will basically tell you that if you will try to create only single principal component, how much information that single variance or single principal component contains. With respect to 2 principal components, how much information you will be able to capture, and so on. So what you can do is you can try to create a graph between the number of dimensions and the EVR, explained variance ratio. And you can see that at any point of time, wherever your graph reaches the information more than 90%, that is where you should stop your dimensions, number of components. So what I'm trying to convey here, let me just show you via writing here. So what I'm trying to say here, for example, in this case, you can see, right, this is something which I would say is 90%. And this part came into picture with the number of dimensions as 5. It means that when we are working with this diabetic model, the number of components optimal value will be 5, via which 90% of information I will be able to retain. Initially, we have 8 number of features, and when we are trying to create the principal components, we should create from PC1 to, you can say, PC5 if we want to retain 90% of information. If let's say you are saying that, I just want to retain maybe 50% of information, in that case, let's say working with only, I would say 1 dimension will also be fine. Sorry, PC1 and PC2, 2 dimensions will also be fine. And here also, it should not be 5, it should be 6. Number of components will be 6 because we are starting from 0. So it will be PC1, PC2, PC3, PC4, PC5, PC6, PC7, PC8. So in a way, we can create 8 principal components. In a way, I would say with respect to this data, we will be, if we want to have a 90% of information, almost 6 PC components we need to create. We can reduce only 2 dimensions from 8 to 6 if we want to get the 90% of information. So this kind of graph will basically help us determine that how much optimal number of principal components we need to create in order to have a maximum information of a given data. So how basically you can create this graph? We will try to use this cum sum. It will try to find the cumulative sum of the explained variance ratio. So you will use this function to calculate the cumulative sum at every point of time. Then you are saying X label is my dimensions, Y label is my EVR. I'm trying to save my figure, and then I'm trying to showcase that figure. So now I think it is pretty much fine. In future, if let's say you want to find out the number of optimal features, you can directly use this particular way to calculate the EVR and then do the cumulative sum of that in order to capture the cumulative information that you will be able to get in every particular component that we have. So this is how basically the internal working of PCA works in terms of implementation. So I have tried to deliver the idea of both of the ways, how we can do manually via 3 steps, and then how you can do via importing the PCA package which is available in sklearn.decomposition. And I hope both of them is pretty much clear to everyone. And even I have tried to showcase you that, how these values are actually similar. Acha, one question which I can ask you as a task, you can see that there is a negative difference. If you will see multiplication of -1 in every value is done. So can you let me know why is that so by referring this documentation? And does that impact our actual value, or in terms of dimensions, how will it differs, right? In terms of absolute values, it is same only. In terms of dimensions, it is multiplying with -1. So in terms of visualization, can you tell me what difference it will make? Or does it make any difference or not? That's the first question which I want to ask from you. So please do your research and let me know. You can reach out to me via email or LinkedIn, and definitely I'll look into this answer, right? So I hope that this part is until so far is pretty much clear to everyone. So now I hope that you will be able to get an understanding that how manually also we can apply PCA, and how with the help of sklearn also we can apply PCA. What is the concept of explained variance ratio? I hope that is also pretty much clear to everyone, which is basically helping us to let us know that what are the principal components optimally which we will use depending upon what kind of data we are working on. With this, our discussion of, I would say, dimensionality reduction is over. Now we are shifting to our next new module, which is about the boosting algorithms. And you will observe that we do have different categories of boosting algorithms in our course. So without wasting any time, let's try to start and jump towards our new journey, where in the upcoming session, you will see all together we are jumping towards a new module of boosting. And I hope that until so far, whatever modules we have covered up, you are enjoying this learning journey with me. Bye bye, everyone, and I'll see you all very soon in the upcoming module.